In this section, we'll continue on with hypothesis testing. With the 10 steps, we'll look more in depth at steps 1 through 3 using the ECMO paper example. So our essential questions for this section are: what is step 1 and why is evaluating the data important? What is step 2 and what are the two main assumptions associated with step 2? And what is step 3 and specifically what are H0 and HA? If you recall from the ECMO example from the Peek et al. Paper about the efficacy and economic assessment of conventional ventilatory support versus ECMO from the Caesar trial in 2009, they were looking at acute respiratory distress syndrome, or ARDS, that had a high rate of mortality with estimates that I found ranging from 26 to 58%, though the paper found different contemporary results. They talked about how mortality increased with disease severity. In addition, that there were other complicating factors. They talked about the standard of care for ARDS as positive pressure ventilation, but recall that that's associated with additional lung trauma. And if we are trying to get the lungs to heal for respiratory distress syndrome, perhaps positive pressure ventilation is not the best option. So utilizing ECMO is going to utilize cardiopulmonary bypass technology, and it will reduce the pressure on the lungs, which hopefully provides a chance for the lungs to heal. The research question posed by Peek et al. Is, does ECMO improve the chances of survival from ARDS? This is a very general question. There's a lot of information left out of this question, and at present is not a question that can be addressed statistically. So how do we do that? We'll go back to the 4 phases of describing or detailing a statistical question, answering it with data. And we're going to look in depth here at phase 1, stating the question. Step 1 is evaluate and describe the data. Step 2 is reviewing the assumptions associated with your data. Step 3 is stating the question in the form of hypotheses. So for step 1, this is in fact the most important step of the 10 steps. Without understanding your data, it will be very difficult for you to answer the question and be sure of making the correct decision from your data. Our goal is to understand the data, and we want to fully describe it. This includes not only the outcome of interest, but any other additional variables you have collected that will help describe the sample. So ask where the data came from. Of course, if you design the study, you'll know. If you are using data that someone else collected, discuss with them, read the paper, read the protocol if it's freely available, to determine how the data was collected and what were the observed statistics. You need to begin by determining if you can understand the underlying population. So what is the sample you've taken from that population? What were the data collection procedures? Are they systematic? Can the data be collected without error? The data should have a specified amount that has been collected. Was it collected over various time points? Was everything collected at the same time point? Like in the ECMO study, there were multiple centers, so there should have been a protocol for data collection to be followed. If there is that protocol, can you determine if it was followed? And if not, what are the implications of that? So an example of what is called a protocol violation is if centers were sent a cuff to collect blood pressure, but that cuff broke and then they manually collected blood pressure. That could introduce different types of errors in the data collection process. You also need to determine the observed statistics from the data. Continuous variables will have statistics like the mean and standard deviation, or the median and the minimum and maximum values. So continuous measures will have something that denotes the center value that was observed, or the middle, and then some sort of estimate of variability or the range. For categorical variables, like we're using in the ECMO paper, we'll be looking at n's, so numbers per groups, and percentages or proportions. For every variable and for your whole data set, you need to understand the n that was originally collected and then the n that are missing values. So how many usable responses do you have? This is very key when it comes to being able to answer your question and then generalize it back to a population. For every single variable you have, not just the outcome of interest, look for errors or outliers, and then any potential observations of interest. So anything that is unexpected. Not all outliers are wrong. So you may have a set of blood pressures collected where it goes from 120 systolic to maybe 175, and then you could have one observation that's 182. And while that's a high observation, it's not unrealistic. However, if you have a systolic blood pressure that's reported as 482, that is an actual impossible value. So you would need to go back and verify that that data was likely entered incorrectly. And then if you cannot verify that, you know that that is wrong, and you need to have a discussion about removing that data point. So look in all variables to determine if there are outliers, things that can be corrected, or anything of interest. Our first definition for this section is a statistic. And a statistic is simply any quantity that can be calculated from observed data. So a statistic is just a number. We will, however, use that statistic to help us make decisions in our questions, as well as make inferences back to the general population. In the ECMO study, they define survival measured as death by 6 months or before discharge from the hospital at any time to the end of data collection. They also further define discharge from the hospital without severe events, but for now we'll just term this survival. So our main variable of interest is a yes or no response, and that makes it dichotomous. There are only two options. They either survived to 6 months or they did not. From that, we can then calculate our proportion noted as P. They noted in the ECMO group that 57 of 90 patients survived. And you can see here that we use the 57 in our numerator and the 90 in our denominator. So the X is the number that survived and the N is the number in that group. And that gives us a proportion of 0.6333, or approximately 63% of those in the ECMO group survived. This is our starting off point for using our observed data to answer the question if ECMO improves survival. Before we can do that, we need to review the assumptions we're making about our data. In this study, the main assumptions are that the ARDS victims that are in the study, the participants that are in the study, are representative of ARDS patients in general, and that each of these patients' experiences is independent of the next. And why is that important? Well, we know the study had well-designed entry criteria. We know that no subjects were excluded for arbitrary reasons, so they didn't just pick the healthiest of the subjects so that they would do well. Their only exclusion criteria were listed that subjects in this study had ARDS and they were unconscious, intubated, and ventilated. So for instance, we would not have enrolled patients in this study that were still able to breathe on their own. And therefore, we can say that this group is representative of ARDS patients that were in similar situations. What about independence? So in lieu of information, we assume representativeness and independence. Unless we're given information that violates them, we're going to go ahead and conclude that things are representative and independent. But we do need to understand that violation of those can have implications for generalization. So just make sure that the units of observation that you have are not related to one another. So no family members, people that are not living in the same house. Though there are possible ways for you to deal with those statistically, in the tests we're going to use, we need to have representativeness and independence. Once we've concluded that we understand where our data came from and that our variables have been collected in a manner that was consistent and didn't produce bias or errors, and that our sample is representative and independent, we can state the question. So what, in statistical terms, is that question? We have a general question about if ECMO improves survival, and we know now that we observe 63.3% ECMO survival rate. But is our observed 63.3 better? Better than what? What are we going to compare it to? In the ECMO paper, they tell us from a case series of patients with severe respiratory failure that survival rates were 18 to 44%. Do we just take their word for it? Do we go out and look up other ECMO survival rates? And the answer is a little bit of both. You want to look at the references that they've given. You want to do a case search to see if there are any additional references, but you do want to make sure that you have a contemporary comparison. That leads you to picking a comparator. If we use the lowest survival rate, so that 18%, then obviously 63.3% is likely better than 18%. But that's not all that we care about. We don't simply just care about saying ours is better. We actually want to have evidence that ours is better. So the 18% was maybe from a long time ago. The patients might have been sicker, or they didn't get any treatment at all. So let's continue to investigate for other potential rates that we can use. This is a warning. It's very important about historical comparators. You need to understand the proportion and where it came from. So this again goes back to step 1. Understand your historical comparison. Pick one that is not relevant and your comparison will be meaningless. As an example, you don't want to compare multiple sclerosis results obtained from studies now to those 50 years ago, because the diagnosis criteria of the disease has changed even in the last 10 years. So using a comparator from 1945 would not be informative to the disease as it is described and understood today. For our ECMO, we want a historical population that did not get ECMO, because we want to show that ECMO is better than standard care, but that they received a high standard of care that is contemporary to the time frame of the study, which was in 2009. So we want to choose a rigorous and meaningful comparison so that when we answer our statistical question, the inferences we make back to the population will be sound and people will believe them. So we're going to use 44%. That was the highest given level at the time of the paper in 2009. So in order to say that ECMO is an improvement over standard of care, we want our observed rate to be statistically significantly different from 44%, the highest rate shown before our study. So that takes us back to our question. Statistically, we can now ask, is 63% ECMO survival better than 44%? The easy answer is yes. Our observed proportion is numerically larger. Obviously, 63.3 is greater than 44. But we're not actually interested in anecdotal or observational conclusions. We want to determine if the difference could be due to chance. We want to know if they are statistically different. Is 63.3 statistically different from 44? This leads us to defining a hypothesis. A statistical hypothesis is one that is stated so that it can be evaluated using statistical techniques. These are the techniques we'll learn about throughout the course of the semester. We're going to continue to answer questions statistically by framing what is called a null hypothesis and then looking at the alternative to that hypothesis. So let's think about what we currently believe to be the true state of ECMO survival. We're going to then state that as our null hypothesis, and then our alternative hypothesis will be the opposite of that. A quick note that the hypothesis is a statement about your population. So we're framing a question about all of those people who have ARDS that are representative of this group that could be treated with ECMO. This is not a question about our sample or our data. We define the hypothesis theoretically before the data is ever collected or before we've ever looked at the data. So we have a question we'd like to answer, and we're going to use this data to answer that question. Once we have our answer, we're going to make inference back to the ARDS population about being treated with ECMO. First, we're going to phrase the hypothesis of no difference. This is the null hypothesis. You'll see it denoted as H0. That 0 means null. It comes from computer programming, where 0 means null or nothing. It is important to note that we are always going to assume the null hypothesis. We will always assume that this is true before we start. The null hypothesis is what we'll test. It is the simplest explanation of events. It is the current status quo. There is no difference, there is no change, there is no improvement by adding ECMO. nothing unusual has occurred in the data that we're looking at, we're going to assume that our ECMO rate is 44%. Our preference as scientists and researchers and statisticians is to believe the simplest explanation for a phenomenon. The null hypothesis is the statement of that explanation. It's also what we hope to contradict. We usually hope to reject the null hypothesis. We usually hope to find in favor of the alternative. When we define the null hypothesis, again, it is the status quo. It is going to be stated as simply as possible in order to make the decision to alter the status quo as clear as possible. We're going to use our observed data to show the difference is not due to chance, or that there is enough evidence to change what we believe. That leads us to chance and randomness. It's a little known 11th commandment, thou shalt not interpret randomness. Randomness just is. So don't make an interpretation about the variability that you see about your endpoint. We need to see if it's random noise. Could be caused by measurement error or chance occurrence. There are many reasons that could account for odd observations. What we want to know is, are there enough observations far away from what we expect to see that we want to change our mind about the null hypothesis? In the ECMO paper, let's assume that any observed improvement over the 44% is purely due to chance. So once people were given ECMO, any result we see that's far from 44% is just random. So we're going to state the null hypothesis in terms of that assumed rate. So one proposed state of nature is that survival is less than 0.44. Then the other possible state is that survival is greater than 0.44. So we can actually state this by stating two possible states of nature. The null hypothesis that the true proportion of survival from ECMO is less than or equal to 0.44. The alternative being the true proportion is greater than 0.44. So we have a null hypothesis with an equal sign and an alternative hypothesis with a greater than sign. They are mutually exclusive events. The two are complementary. One and only one of the two hypotheses is true. The alternative hypothesis is often called the research hypothesis. That is often what you read in the paper at the beginning of the paper or the beginning of the results of a talk or a poster or an abstract. Researchers are trying to show that they believe the new state. They're trying to show that they believe the alternative. Because we can't prove anything, that is, there's no possible way to sample the entire population, and we're going to be using our sample as evidence, we're going to, quote unquote, prove by contradiction. So we're going to choose between a simple model, the null hypothesis, or the new model. We're going to choose to trust the data in the alternative. So we won't prove the null, we won't prove the alternative. We are either going to accept the null or we are going to reject the null. We can fail to reject the null, so we won't change our mind. We can reject the null and accept the alternative. So remove the word prove from your statistical vocabulary. How is it that we're going to do this? So as you saw, we are going to collect some data, we're going to assess that data, and we're going to answer a question. The question has to be a statistical question. We will define the state of truth as the status quo, and then the contrary state of that. The truth will be the null hypothesis, and the alternative is going to be the opposite of the null hypothesis. We will then collect our data, or if the data has already been collected, we will take a look at the data. We will then assess the likelihood of observing the collected data, assuming the null is true. Remember, we are operating under the null hypothesis. As far as we know, with the ECMO study, the best rate of survival from ARDS is 44%. We're going to use our data to look at the likelihood of observing something that is greater than 44%. If the observed data is what we expect within some reason to see, then we're going to continue to believe or fail to reject the null hypothesis. However, if our observed data is far away from what we expected to see and has been collected with some rigor, then we are going to cease to believe the null hypothesis, we are going to reject the null hypothesis, or we are going to conclude the alternative hypothesis. There are only two options in statistical testing. We're going to start by assuming the null is true. We're going to use our data to make a determination if we continue to believe the null hypothesis or if we change our minds to believe the alternative hypothesis. In this section, we reviewed steps 1 through 3 in the context of the ECMO study. In step 1, we evaluated and described the data. In step 2, we assessed the assumptions of representativeness and independence. There will be more assumptions that we need to assess as we pick our statistical tests. But for now, just make sure that your data sample is representative of the population at large and that you don't have dependent units of observation. And in step 3, we learned about defining the question statistically. We have our null hypothesis, that's our current state, and we have our alternative hypothesis, and that is our research question. And we will ultimately use our data to pick between the two. So up next, we'll continue with the 10 steps, but before we can answer the question, we need to decide how we are going to answer the question. And that involves steps 4, 5, and 6, deciding upon a summary statistic, a number that reflects our question, and in this case, we'll be using the proportion. How could random variation affect that statistic? And then we'll make a decision rule, how we'll choose between the null and alternative hypotheses before we actually calculate the information to help us decide.